right. I think we're ready to start. Okay, welcome everyone to the Trottier Observatory, the virtual Starry Nights tour with your hosts, myself, Kyle, and joining me,
Julia, for the first time.
Oh, we got a new person. And also with our moderators today is Nat Jet and Matthew, longtime veteran staff members here at the observatory. And we're going to put on as best a show as we can. Now, this is kind of what we do once a month, just to allow people who may not have the means to visit us in person on other Starry Nights up at the Burnaby campus at SFU. So this is kind of a nice way that we could bring Starry Nights to more viewers across the Lower Mainland here, Tri-Cities. What can we start with here? Well, on the itinerary, we got lots of star clusters we're going to show you. We have some awesome nebulae as well as hopefully by the end of the night, when it raises a little bit higher, we're going to try and look for Saturn as well. It's always a pleaser for people that come up in person. And it's also really interesting in this particular time in its orbit because it is at such an angle that you can see the rings nearly edge on. It just kind of looks like a toothpick going through the planet there. Anyway, it'll be kind of cool. But to start off, just in this nice dense star field here, we're looking at the small Sagittarius star cloud called M24. Located just within the Milky Way itself. And as you can see, and like the main cluster is just kind of right here, this big bunch of stars here. Again, these stars are quite a range of distances, with kind of the larger ones being, maybe 10 or 20 light years or so, kind of like this nice bright one right here, ranging to maybe a couple hundred light years away or more. And then you get into the thousands of light years away. Mm-hmm. Right, because we're staring right through the disk of the Milky Way, our home. Mm-hmm.
Yeah. So, as a little bit of an introduction to the naming conventions we have here, for those of us that aren't too familiar with how things are named in astronomy, so this object, it has its casual name, so the small Sagittarius star cloud, but also has the listing M24, which stands for Messier 24, which means it was the 24th object listed on the Messier catalog. So that means back in the 18th century, an astronomer named Charles Messier was compiling a catalog, a list of all of the cool deep sky objects that there are out in space that he could see. And so he was just listing them one by one. The first one's actually quite famous. It's the Crab Nebula, so that would be Messier 1. And 24th on the list, he put this wonderful star field, Messier 24. So if you're wondering how these things are named, so what does it mean if it's NGC 6024 or anything? It's just other catalogs.
Yeah, I think NGC is New Galactic Catalog, right?
Yeah.
Mm-hmm.
There are many of them. Messier is one of the most common. It has a lot of the brightest objects that we could see in the sky because it's one of the earliest. So all of these objects were found using still rather early telescopes. So if you're wondering if an object would make a good target with your home telescope, or maybe even a good pair of binoculars, the Messier catalog is definitely a promising place. So if it has a Messier designation, it might be a nice thing to try. And things like these, star fields, do make a good first target, because we've got all of these bright stars. There's a lot in one area, so if you maybe want to take your binoculars out one night and have a little look, then it's a good place to start.
Yeah, and very pretty to look at too, I think, as well. Definitely it owes to the richness and vastness of the cosmos when you look up into the night sky. And also, I thought I'd mention this as well, where because this object is located in the Milky Way, you can see there's so many stars. And before humans as a civilization really turned telescopes upwards, they actually thought the Milky Way was actually like, well, not a liquid, but more like one solid streaming thing going through the sky. And the Milky Way, the name, I think, comes from Egyptian history and culture as well, where it was one of the creator deities that stretched across the sky, and because milk is a nourishing liquid for lots of life forms here on Earth, it was called the Milky Way. But it wasn't until Galileo and other early astronomers, when they turned their telescopes up to the Milky Way, they made out these individual stars, and it became really eye-opening to them. It's been really, really fascinating. But seeing the vast richness of like this always kind of puts things into perspective for me, at least. Because perhaps on one of those stars, there might be another civilization looking back at us and wondering the same thing. Mm-hmm. I don't know. Anyway. But yes, so this is M24. And I think we'll continue on with our list here. Okay.
Maybe Messier 52.
Yeah.
Or go to something slightly denser and further away.
Exactly. Okay, so we're going to hit warp drive here, ladies and gents. And we're just going to slew the telescope. All right. So we go like this. We go like this. And yes, please feel free to ask questions and comments in the live chat. We love hearing from you, just as much as we love answering questions from you as well. Mm-hmm. And yeah, you can see on the cameras here on the left that we have our dome rotating as well. And again, for really hearty astronomers, SFU is not really the best place to put a telescope because of some of the light pollution that comes from Burnaby, Vancouver, and places like that. But that is not the main purpose of the observatory here. It is mostly for outreach events like Starry Nights and tours that come up, as well as sometimes for use for some of the students that are up here as well, to conduct research and stuff. So I go like this, I go like that.
Excitement is palpable.
Oh! Okay, so now I gotta fiddle with the little filters here, like this. I'm gonna go like this. Okay. Ooh, so, okay, this is interesting. I wonder where we're looking at here. So if we look at the ops screen, okay, and sometimes when taking observations, you can see that some of this glare from some of the lights kind of leaks into our cameras here. And you can see that by just that little bright section off to the right of the image here. Just on the side. Sometimes some stray lights do make it into the camera, and we have to be wary of that. But this is more of a demonstrative exercise, so this is okay. But here we have another star cluster, M52. Let me just bring some of this stuff. Yeah, M52. Also called the Scorpion Cluster, and it's located in the constellation of Cassiopeia.
Yeah, I don't know about you, but Cassiopeia, she always reminded me of just a big W in the sky. So if you pull up your stargazing app, or even if you pull up a map of the sky, you will search for a constellation called Cassiopeia, and it's supposed to, I believe, represent a throne or a chair that the mythical princess would be sitting on. But in general, I find that it looks like a big W. It's very well visible in the northern sky throughout the whole year, and it's a wonderful place to have this target. Surprisingly, it is not in Scorpio.
No, even though it has that kind of name to it, right?
Yeah.
Ugh. But going towards your point on seeing a W and stuff, humans are all about seeing pictures and patterns in the sky, right? Which leads to some of these are the stories and images that we make when we look up at these different constellations. So it's always awesome to read about and experience these constellations and storytelling every time we look up into the night sky.
Yeah. Mm-hmm.
So yeah, Cassiopeia is one of them.
Yeah.
What's another really good one?
I mean, here's the thing. The whole section of sky that Cassiopeia is in, it's got a bunch of characters from the same mythology. So in the same region, you could find the constellations of Andromeda, you could find the constellation of Perseus, the mythic hero. So in that whole region, we've got a theme going on of just Greek mythology. And then, what are the others? So Orion, the hunter, he's in the sky, another Greek mythology character.
Yeah.
And then, let's see, I don't know, do the Big and Little Dipper have any stories behind them?
Big and the Little Dipper. Oh,
the major and minor.
Yes, well...
Mother and child bear walking across the sky.
Yeah, the one that comes to mind for me is that Ursa Major, the mother bear, is trying to protect Ursa Minor from Draco.
Oh,
because,
that's interesting.
Yeah, because the constellation kind of snakes through the two. Mm-hmm. So it's the mother is trying to protect her baby. That's where that comes from. Yeah.
All right.
I don't know, but a little bit more about this object here. Okay, so one thing that you learn about right away when you get into astronomy is how far away everything is, and how
large.
Large
size.
And how large everything is. Holy smokes. So, this star cluster is about 4,600 light years away. So you're seeing it as it was 4,600 years ago. And I think that's when the pyramids were being built.
Sounds about right. Yeah. So it's crazy to think about, but essentially what a light year is, it is the distance. It's not a length of time, it's a distance that light could travel in a year. So light is the absolute fastest thing in the universe. And so a light year is the furthest one could theoretically travel in a year. And so it takes the light 4,600 years to travel from these stars to us. Absolutely crazy. That's why we're seeing this as it was 4,600 years ago. Now, the size of this thing, it is approximately 10 light years across. So, following the same logic, if we have a star on the right side of this cluster, and it beams light to another star on the left side of this cluster, the second star is only going to receive that light 10 years later. So if two alien civilizations were trying to communicate across this star cluster, they would have a delay in their messages by 10 years. They'd have to be very, very patient.
Oh, yes. Holy smokes.
Mm-hmm.
And for just a little observing tips of this is you are able to see this cluster, as with many others, with binoculars, but it does have to be, of course, very, very dark. With it being summertime, we don't have the best, like, dark skies, because, of course, longer days, shorter nights. Mm-hmm. But you do have to utilize a star hopping technique to get to this cluster. So, star hopping is essentially using recognizable stars or constellations to help guide you to another place in the sky. Very useful for learning the sky, I think. I remember I got a motorized, computerized telescope when I was much younger, and it was really awesome because I get to punch in what I want to look for, and it points right to it. But I didn't really learn the sky.
I had the exact opposite experience
Oh!
Because I got a motorized telescope when I was young, and it came with an app and everything, and you know, you could just punch in what you want to see and it'll take you there. However, my app, it did not work awfully well. And so what ended up happening is that I started looking at easier targets, and then from there I had to hop to the harder ones. So out of necessity, I was forced to learn.
Oh, okay.
Yeah.
That makes sense too. That's fair. That's fair.
Mm-hmm.
Well, yeah, there you go. Experiences vary, definitely.
Yeah.
One recommendation I always give to new astronomers is computerized telescopes, of course, are more expensive because of that accessibility in there. But I feel it's better to get a manual telescope. They're cheaper, actually, as well. And also, you can get, you can use apps as well to help you learn the sky and try and put like what you see on the app up into the sky. Definitely helps with learning. And you can purchase all sorts of books and literature that can help you star hop as well.
Yeah, totally agreed.
Mm-hmm.
Yeah.
It's been pretty cool. But just to go back to the star cluster here, again, fantastic object. Very, very long time ago that the light left this cluster, and it's a little bit more open than a lot of other clusters that we might see later tonight. One being that, okay, because it's so open, it's indicative of how old the star cluster is. The more spread or diffuse the star cluster is, the younger it is, because you need time for the stars to gravitate toward a common center. But older stars like M13, or star clusters, like M13, of course, are much older because they're more dense.
Yeah. So maybe at this point we will move on to a denser object,
Ooh.
and you guys will be able to compare. So this is an open star cluster, and it's one of two kinds. There are open star clusters, which are young and diffuse and kind of just a blobby shape in the sky, and then there's going to be globular star clusters. Now those are much more densely packed. They're going to be older, and I mean considerably older. I mean like 10 billion years old. I mean seriously old.
Like as old as the galaxy is old. Like it's crazy.
Old. And because of their age, they will be a much more defined shape. They're called globular because generally they're round, they're spherical looking. And the stars within them you will find are older, which interestingly will mean that they will be a different color most of the time.
And we might be able to see that with this one. So from the previous star cluster, M52. Yeah. M52. I'm just going to deviate from the itinerary for now because I just want to quickly show you a really dense star cluster, M13. Which, if you're regulars at Starry nights, then we frequently view this one because it's so awesome.
Yeah, it's literally called the Great Globular Star Cluster.
Yeah.
That's how good it is. It's a Great Globular Star Cluster in Hercules. So Hercules, yet another Greek mythological figure with a constellation in the sky. Anyway, this wonderful globular cluster is found in that area. Now, let us be blinded by its majesty. Whoa. Oh, let's tune those settings.
Oh my god!
Oh.
It's so beautiful.
Oh.
Okay, so we're gonna go like this.
It's almost like a picture of a star made up out of other stars.
Right?
Yeah, but no, it's bigger. It's bigger and better.
I've always heard it being described as like a dash of salt on a black background.
Sprinkled there onto the ground.
Just like that. Look at that. Okay.
Gorgeous.
And again, to give you more scale, the previous one, M52, is 4,600 light years away. M13, Hercules, is 13,000 light years away.
Yeah, the distance is absolutely insane. So many globular clusters, where are they in the sky? Well, they hang out just outside of our galaxy. So if our galaxy is just kind of the shape of a plate, it's a plate floating in the sky, well, then these globular clusters are like little Christmas ornaments for some reason rolling around it. So they're just hanging around the edges. Not part of the galaxy, just kind of next door.
That's a good way to put it. Christmas ornaments that are just kind of hanging out.
Yeah.
I kind of like that.
Uh-huh.
Mm-hmm.
And I mentioned that globular clusters, they're going to be much older than the open kind. So, let's see, the previous one that we listed, Messier 52, we said that it was an estimated 158 million years old. Now, don't get me wrong, that is a big number. 158 million years. I think that is before humans even started evolving. It's before a lot of stuff happened.
A lot of stuff happened, yeah.
However, the one we're looking at now is an estimated 11 billion years old. And now we're talking, the universe is an estimated 13.8 billion years old. This thing has been around for most of the universe's lifetime. It has been there since day dot.
Mm-hmm. Yeah. And just to owe to the life or evidence to support this is, of course, there's a couple blue stars in the field of view here, but most of it is red, orange, and yellow stars as well. Very, very old stars and very, very compact.
Now, why would the color of the star matter when determining the star's age? What can the color tell us about the age?
Okay, so color usually tells us how, well, essentially, how hot it's burning its fuel. So, blue stars, okay, think of it like a stove. If you were to theoretically turn on a stove and, like, you know, turn it beyond high level, essentially, the color would change from red to yellow to white and then blue. Mm-hmm. Now, of course, you wouldn't touch this kind of thing, but because, of course, it gets very hot at red. But once it hits blue, it is so hot. It is incredible temperature. And because of that, it's burning through its its hydrogen so quickly. And so it doesn't last as long. It'll burn through its hydrogen fuel so quickly, it'll erupt as a supernova and die. Red stars and yellow stars are much cooler, and they burn through their fuel much more slowly. And so they last for a considerable amount of time. Hence, mostly red and yellow stars in the Hercules star cluster. But, okay, I just wanted to leave you with that little tidbit. Let's kind of regain our composure, because I know this can be very mesmerizing. But let's return to maybe another example of a star cluster. So let's go to M71 Angelfish, and let's see. So let me just boot this up here. And we go like this. How'd you get into astronomy, Julia?
How did I get into astronomy? So, when I was younger, I mean, I did get to see a lot of the beautiful pictures that the Hubble telescope created, and then I started getting interested in science as a whole, and my most favorite kind of books to read were always the ones about space. So, started reading about astronomy, started reading about the planets, started reading a little bit about cosmology, and I was just mesmerized at the size and scale of these things. So as humans, we live in a very tiny corner of the universe, and so we spend a lot of time studying this tiny little area, and then if you start reading about astronomy, you discover this whole big beautiful universe out there for you to explore. And so after that, I got a telescope and I started looking, and I've been trying to delve deeper out there ever since.
Kind of a rabbit hole this field can be, eh?
It can almost be like, it's like the opposite of a rabbit hole. It's like a rabbit who's always lived in its little den and gets to go outside for the first time, and it's just like, oh, I have to look at everything that's out here.
We have to know more.
We must know more. Show me every tree.
Yes.
Every lake, every blade of grass.
I must know more.
Yeah.
Oh, man. Anyway. Yeah, and I love, that's one of the great things about doing Starry Nights, is I love hearing stories from people who got into astronomy as well. I mean, a lot of people also got in from seeing Saturn for the first time.
Oh, yeah.
And that was kind of one of my experiences as well, where I was over at my cousin's grandfather's place in Nova Scotia, in a little town called Truro. And he had built his own observatory in his backyard, kind of smaller than what we have here, of course. But it was during the Perseid meteor shower in August, and it was like every minute there was a meteor. There was no light pollution, and it was just a sky full of stars. We looked at Saturn, we looked at Jupiter. I was like, I want to learn more from this. So I did just what Julia did as well. I got myself a telescope, dived into all sorts of books and literature, and the rest is history.
I mean, it is such a pleasurable part of this job to reintroduce people to the sky and get to just relive that moment again and again, the discovery for the first time. I mean, I just recently was on the Sunshine Coast and on Vancouver Island, and I was somewhere where the sky was very, very clear and the Milky Way was visible, and I had a friend with me, and I dragged her out to the beach. and it was very late at night, and I dragged her out to the beach, and I said, look at this. And she'd never seen the Milky Way before.
What?
Yes, and she hadn't ever seen shooting stars before. And there you were seeing one, you know, as you said, about every minute. So she got to see satellites, she got to see shooting stars, she got to see the Milky Way, and she got to see Saturn. I gave her a little tour of the constellations, and I mean, I'd say she had an excellent night just because it's the first time experiencing the sky to this level. But I had an excellent night too, because I got to feel that enjoyment again of just seeing it for the first time through new eyes.
Oh, man, I love it. Astronomy sometimes, at least for, unfortunately, if you live in the city, it can be quite difficult to actually find really good spots to look up. Or rather, there's not a whole lot of bright things to look at in the night sky when you're in the city. So it can be quite difficult if you live in the city to find a nice spot. And I'm just looking in the chat and seeing that there's been a discussion on really good places to look for like dark sky. And I think who mentioned it? Yeah, Dr. Joanna Wu talked about Aldergrove Park. Great place to go. Yeah, Cypress Mountain, Porto Cove, places like that. Just like, okay, it doesn't really matter the park or the place that you go to. Just what matters is you're far away from light pollution and city lights.
Yeah.
And then you'll be okay. You'll be okay. Oh my gosh. Okay. So we diverged a little bit there, just to give a little intro to ourselves. But here we are. We've arrived at M71, the angelfish globular cluster. Once again, this is another dense-looking one, as evidenced by that dense nucleus there. It's about 13,000 light years away. Another fantastical distance. And it's approximately 26 light years in diameter. And again, this globular cluster is really, really old. It's very dense. There's lots of red stars. So there's about 9 or 10 billion years old.
Yeah, so not quite as old as the Great Globular Cluster, which we mentioned was about 11 billion years. But this one is still 9 or 10 billion years, still most of the lifetime of the universe. These globular clusters are very, very old.
Oh my gosh. So old. But yes, so things with star clusters, and this will be kind of the last thing, and we'll just kind of diverge into some more colorful objects. Okay, with star clusters, there's approximately two main ways okay, I'm getting too excited, that they may form. One of them is maybe there was a nebula or collapsing gas cloud that made maybe 2 or 3 stars that were really close to each other. And that created a strong gravitational well that, pulls other stars closer to it. And over the eons, that makes a stronger and stronger gravitational well that pulls more and more stars. And of course, this process takes a very, very long time, but that's one of the main ways that it can be made. Another way is maybe there's a one or two black holes at the center that pulls stars toward a common location. But the main idea is it takes some sort of high gravitational pull from something at the center to pull these objects, or rather these stars, close to each other. Really quite fascinating, and I think still a very active area of research in the astronomy community right now. Pretty kind of cool.
Incredible.
Things are happening all the time.
Yeah. Now, all right, we've shown you quite a few star clusters now, and we don't mean to drag on with them. It's just that they're so beautiful, and we love them very much, and we do like talking about them as well.
Yes.
But
we have to peel our eyes away.
Yeah.
Okay.
So let's talk about a new kind of object. Let's talk about nebulas. So nebulas are what we call clouds of gas in the sky. So this time it's not stars. It's not our good old friends, the stars, like the sun emitting light. It's clouds out in space. And back in the day, actually, when telescopes weren't quite as good as they are now, we used to call everything that we saw that was far away enough to be hard to see a nebula. We used to call galaxies nebulas. Some star clusters were called nebulas because back in the day, through an old-timey telescope, everything was kind of cloudy when you looked at it. Everything was kind of blurry, so we called everything clouds, or nebula in Latin. Now we've updated the terminology and we found out, okay, some things are galaxies, some things are star clusters, but these clouds of gas, they have retained the name, and now they're what are officially called nebulas.
Back in my day, they were just clouds of gas.
In the 1800s, when I was born.
Oh my gosh. Okay, first object we're trying to look for here is called the Elephant Trunk Nebula. Okay, now this one is kind of difficult to see, even on a good night. So.
Oh, we're starting
be...
with a difficult target here, folks. So.
Hey.
Send us help through text.
Yeah.
Help us out.
We're astronomers. We're ambitious individuals.
Yeah.
We love seeing awesome things. Now, it might take maybe 2 or 3 frames to try and find the elephant trunk.
But
I think.
Or the lack.
You know what?
I see the lack. So.
I think that's part of it, right on the edge there.
This definitely is.
Yeah.
So the thing that you need to know about the Elephant Trunk Nebula is that's what's called a dark or absorption nebula. Now, this kind of nebula works a bit like clouds on Earth do. So it's a cloud of gas, and when it passes in front of a group of stars, it's going to just absorb their light and block it from passing through, which means that it will appear right now on your screen as a place where the stars aren't. Now, instead of searching for where stars are, we're looking for the place where they are not. And kind of to the right of the streaming window, you could kind of see a lollipop shape maybe, as we fiddle with the settings.
Yeah.
A dark area where the starlight is being blocked.
Apologize, folks. Just trying to get as good of an image as we can. But I think that's looking good. Maybe I'll take a few more images. So what we have going on here in this program is we're taking an image every 20 seconds. And then it's taking that image and stacking it on the previous one to try and make a better and better image, essentially. That's why, and just looking at the chat, this reminded me that in the last object we were looking at, the star cluster, maybe a few of you noticed that there was a streak that went by. Usually due to satellites, unfortunately, that was streaking by during that one particular image that when we took, stacked on top, and then we have a streak through the image there. So kind of meh. Okay, I'm going to do something daring. I am going to try and orient the telescope so that maybe this elephant trunk is a little more centered. So bear with me. as I work my magic. Okay. So if you're over there, and the thing is, this is a reflecting telescope. So sometimes, or in fact, actually, left is right, right is left. Everything's kind of opposite. So if I want to move left, that means left on your screen, I gotta move to the right. Maybe a little right down. And let's see how we do. Okay, okay. Let's see if I screwed it up. No. Oh. We hit warp speed.
Oh. Stars are flying away.
Stars are flying away.
Come back.
Oh, okay. So we'll see another example of this in a moment. Uh-oh. Uh-oh. Okay. I might have went the wrong way. Okay, let me go the other way. Let me go this way. Because we want everyone here to have the best quality experience, right? When looking at these brilliant structures in the heavens. We'll see. Okay, yeah, so what I was saying is we'll see another example of this in with our next object, but there are two different types of nebulae. One of them is called a stellar nebula, so that's like your Orion Nebula, your Elephant's Trunk, and essentially other nebulas that are giant gas clouds in space. And essentially, they're the stellar nurseries, or the birthplace of stars, and they're essentially the starting position. The other type are one's called planetary nebula, where they essentially arise from the corpse of a star.
Oh, that sounds very macabre. Maybe I'll expand on that a bit more so it sounds
yes.
less Halloween. But if you think about the lifespan of a star lives by using up elements within its core. So it keeps on fusing lighter elements into heavier ones, like hydrogen into helium, until it no longer can. And at that point, it is going to go one of two routes. If it is heavy enough, it is going to go supernova. So it's going to launch a bunch of gas out into space, into the spread out area, and cause this large, bright, glowing area of gas, while the rest of the star, the core, is going to collapse into a very, very dense star, usually a neutron star, or if it's even heavier, maybe it'll form a black hole. However, if a star isn't quite massive enough to do all that, it'll still eject a lot of gas. However, it won't fly quite as far. Instead, this gas will form kind of a spherical shell around the star, and then the rest of the star will collapse into a star, usually a white dwarf. You could think of these kind of next stage stars as a new part of the star's lifespan. It's been transformed like a caterpillar into a butterfly. It's in a new life stage. But anyway, so these spherical shells around the lighter dead stars, that is a planetary nebula. You can recognize them because they're very, very round, like a planet. So when they were first noticed, it was thought maybe there's something like a planet, because planets were the one thing that we were sure they were round. Stars are points, planets are round things, and that's how we name planetary nebulas.
Mm-hmm. I tried. Didn't really work.
So, well,
I brought it back.
There it is, in the corner.
And I think this is the head, so I think a few have pointed out that this is like the eye, so to speak.
Okay.
Yeah.
I'm embarrassed to say that I have been misinterpreting the Elephant's Trunk Nebula this entire time. genuinely, turns out that this is the head, these are the eyes, and maybe this long part is the trunk. I genuinely thought this entire nebula was just supposed to be the trunk, and that this is just kind of this trumpet shape was just an elephant's trunk pointing upwards, and here it is blowing a beautiful song or something into the sky. Well, I have learned today.
Hey, I mean, we see different things. We see different pictures.
Yeah.
Part of it. And also, I'm sure you all can see now, we have satellite 1, satellite 2 going through our lovely photos here. Okay. So we've been preaching a lot about these planetary nebulas. So this is a stellar nebula, elephant's trunk. So this is where stars are born. And some of them, of course, are very, very dim, and you can see that are inside. The James Webb Space Telescope, with its infrared capabilities, can actually penetrate the gas clouds and actually see the stars inside. So, has it taken a picture of the elephant's trunk?
Elephant's trunk? Well, I could double check, but essentially...
Okay. Oh yeah, go ahead. In the meantime, I'll move it to our next target. Okay, go for it. Sorry.
Yeah, so the thing about these gas clouds is that they effectively block what we call visible light. So those are all the colors of light that we can see as humans. Oh, that's unfortunate. That means when the clouds are out, we can't see the stars. However, these clouds of gas are not as effective at blocking infrared light. So you could imagine that as a wavelength of light which is redder than red, a little bit longer in wavelength than the color red. And so that still goes through these clouds of gas in space. And so if you have a telescope that can see infrared in the same way that humans can see other visible colors, well, then you will still be able to see the stars through it. Now, I am looking at pictures right now. I am looking at a very beautiful image.
Yeah, so we're just looking at that bit.
Yeah. So if anyone feels like it, you could look up James Webb Telescope, Elephant Trunk Nebula, and you will see this beautiful picture where the nebula itself appears to be a red cloud, and through it you could see blue stars, and you could actually see the stars through the cloud. And that is the magic of looking in wavelengths of light other than those that we humans can see. There's information hidden in other wavelengths of light that we gotta search for using specialized tools. Oh, wow.
Look at this.
Now yes.
Look at this.
More of that, please.
Alright, now I'm gonna play with it. Okay, I gotta make it look nice. Whoa.
Expose that thing.
Yeah. Okay, maybe I do this. Oh, not really.
There we are.
Something like that. Okay, as we're all being amazed at this brilliant object, this is the Ring Nebula. Planetary nebula located in the constellation of Lyra, which is also where Vega is, the star Vega. Located just like below the little trapezoid.
So
of the constellation.
Yeah, the constellation of the Lyre. It's like a little diamond or trapezoid, and then there's one more star forming a little handle to that. That star is Vega. Very bright star. It used to actually be our North Pole star for a while, well, 13,000 years ago during the last ice age or so. But now we've moved on to Polaris. Vega's just hanging out there. And so in this constellation we find this beautiful planetary nebula. And you guys can maybe see what I was talking about that spherical shell of gas. So you can see the spherical shell of gas, and you can see that there's almost layers of gas happening. So there's an outer layer of red, and then an inner layer of something that here appears whitish but maybe appears more yellowish to you guys on your displays. Then there's an inner layer of blue. So what's happening there is that the star, at time of explosion, at the end of its life, had numerous different gases composing it. And so when it exploded, it launched these gases different distances depending on how heavy they were. So light gases, for the star, throwing out a light gas was a bit like throwing a baseball. It was easy. It could throw it very far, and so the light gas ended up as the outer layer. But the heavier gases, it's more like throwing a bowling ball, and they didn't quite get as far. So the inner layer of blue maybe is probably a heavier gas. At the very center of this thing, like the pupil of an eye, you could see a bluish dot, and that is probably the remaining bit of the star that created this nebula. It is a white dwarf star, all that remains of the original progenitor star.
Mm-hmm. That white star right at the center, and this radiation that's being emitted by that white dwarf, it's not fusing anymore, but all of that radiation that's still coming off of it is exciting the particles that are in the nebula itself, which allows us to see it.
Yeah.
And those lightweight atoms that Julia was talking about, those are like hydrogen and helium, and they characteristically they show up as this red color. And things like oxygen and nitrogen, kind of the more heavier elements, they would show up as these bluer colors here.
Yeah.
Mm-hmm.
And to do some comparison of size and distance with the objects we've seen before, this nebula is about 2.6 light years across. So it is smaller than the clusters we have looked at, which, as you remember, were in the tens of light years across. This is smaller because, you know, star clusters, they're made up of many, many stars. This was all created by just one star, so we could forgive it for being a little bit smaller, not covering quite as much area.
Mm-hmm.
And
one thing I want to say, because I just noticed this question in the chat. When did this star explode? Well, we have an approximate number, because the thing is, with a lot of supernovae that are close by, astronomers can take photos of it over decades or long periods of time. And you can get a map, or rather calculate how fast it's expanding, and using that, trace back how old it is. With the Ring Nebula, it's about 2,000 years old. Not very old. And it didn't really explode as a supernova. It just kind of let off its outer layers.
yeah. You could think of that as like a weaker, not quite version of a supernova. Kind of trying for the same thing, but not quite doing it. And
Yeah.
So, as we said, this object's quite young by space standards. To us, 2,000 years is a lot. However, when compared to the globular clusters we saw that were billions of years old, this is a baby, very, very young.
It's a baby. Oh, and this is probably what our sun will become when it reaches the end of its life. A planetary nebula just like this one. Again, it won't explode like a supernova, but I mean, for us, it'll still be destructive.
not optimal, perhaps.
Not optimal at all. Okay. Sorry, go ahead. I'll move to the next one here. So cool.
Yeah, or maybe go look at another planetary soon.
It's close by.
The weather forecast for our sun, its life forecast. Before our sun does any of this planetary nebula stuff, it'll probably first swell in size a little bit and probably turn a darker red, because as we mentioned earlier on in the stream, so as stars age, they often become redder, and that they often become cooler as well. Those two things are tied. Redder stars are cooler. So it's going to swell, it's going to get dangerously close to us with its surface, and then only after it's done that and finished fusing all the elements it can inside of it, then it will finally create a planetary nebula.
Ooh, this one's cool. Okay. Another example of a planetary nebula. This one's called the Dumbbell Nebula. For it looks like a dumbbell. Again, same principle. So we have different colors for different elements.
Nice.
And actually, do you know what? I'm just not going to touch this one because this one looks pretty good. You can see the nice, beautiful white dwarf in the center. That's looking great. Lots of blues are now more sparse and intermixed. Actually, so is the reds as well. But again, another example of planetary nebula. And it was just an honest mistake by astronomers who were just looking up into the night sky and they see something round. Did you mention this already?
Oh, why they're called
Yeah.
planetary?
Yeah.
A little bit. I alluded to
Oh,
it.
okay.
So an honest mistake by astronomers. They looked up into the sky and they saw something that is round, and they looked through their list of objects that they knew of, and there were stars, which were points, and then there were planets, which were round, and then there was everything else, essentially, which was cloudy. So when they saw something round, they said, okay, we'll name it after planets. They're the one thing that we're sure that are round out there. Oh, well.
Were they sure? Well,
yeah, they're doing their best.
to the best of their ability, yes.
Yeah, but we must consider that, for example, the Dumbbell Nebula, was the first planetary nebula that Charles Messier ever found. So it was really early days. So this beautiful object is the first of its kind. It is about 10,000 years old, so it's about 5 times older than the previous target. And it is also about 2 light years in diameter, so you can see the relative size of these things. They remain rather small. And the little star at the center, that bluish star, the white dwarf, that is all that remains of the star which created it, it has about a radius which is about 5% of the radius of the sun. So it's 1/20th the radius of the sun.
5%. Because the sun, I think, is 1,000,000 kilometers across, I think. About. Give or take 1 or 2 million.
Astronomy
so,
errors.
Yeah. So 10% would be 10,000 kilometers across, and then 5%. So this is about 5,000-ish kilometers across.
That is
something like that.
Comparable, honestly, to the Earth's radius, which is disturbing. So that star in the middle, it is about the size of a rocky planet, which is insane. So it really shows you how much a star had to collapse in order to form this planetary nebula. So much of the original mass of that star is just this cloud of gas. The little white dwarf in the middle contains barely anything.
4, 5, 6.
Yeah. Now this is a wonderful target for your own home telescope. If you guys have telescopes.
Hold on, math correction.
Oh, no.
100,000 is 10% of a million. Jeez.
Ooh.
We're okay. We're okay. So 100,000 kilometers across, 10%. So now we're thinking about 50,000. Okay, much bigger than the Earth.
Respectable.
There we go. Okay, we got there. We got there, folks. Okay. So I was thinking about that. I was like, oh, that's a little interesting.
That sounds dangerous.
Neutron stars and black holes could be that big.
Wow.
Which are much smaller. But yeah, pretty neat. But yes, planetary nebulas, lots of cool things. The name stuck, not planets. We're good.
No.
All right.
Let me double check one thing. It's been a while since we've seen any planets lately, and I've been hankering for a little bit of planet viewing now.
Ooh, okay. Let's be ambitious before we go to planets. I just want to try one more thing.
Ooh, what's gonna be?
We're gonna be ambitious astronomers here at the Trottier Observatory.
We always are.
Let's see if it works. I'll leave it as a surprise.
No hints to what this is gonna be. I think I know. I hope it is what I think it's gotta be.
We'll see. We'll see.
Yeah.
Because
Come on.
we've talked about star clusters. We've talked about nebulae. What's the next step after that, I think? Okay, well, the dome is still rotating, so you have to wait maybe like 3 or 4 seconds.
Yeah. The suspense is unbearable when it comes to the telescope moving.
Palpable. It's palpable. Yeah, and sorry about the white screens. That's because the camera is taking in light from the ambient light from the dome, essentially. So because this is 20-second exposures, it's gathering a lot of light. Even though it's dark in here, in the observatory here. Look go. It still collects a lot of light.
Now,
This is gonna be a good one.
come on. Let's have another image. Oh!
Look at this.
Yeah,
Look at this.
There it is. Completely new type of object.
We saw the little things. Now it's time for the big things, I think.
Let's get much bigger. Enough of this 2 light years across. Let's have hundreds of thousands of light years.
Yes.
Now, we will finally reveal what it is that we're starting to look at now. This is Messier 51. It is called the Whirlpool Galaxy. Now, I'm saying galaxy singular as if there's only one of them. Now, if in the bottom corner of your display you may be currently seeing a little bit of an extra glow. So you're seeing the main part of the galaxy.
Yep.
You're seeing the big spiral.
Give me a moment. I'll try and make it better.
Yeah, but at the bottom there's another glow, a suspicious shine. What's that? What's that? Well, that's Messier 51 part 2. It's Messier 51b. So this is actually an object which is 2 galaxies. The big spiral you're seeing is Messier 51a. It is the main Whirlpool Galaxy. The little glow, which hopefully, a bit too
well,
there it is.
That's fine.
You can see it.
We'll move back.
Yeah.
In a bit.
That secondary glow is a dwarf galaxy, Messier 51b. And these are 2 galaxies that are very, very close to each other. And so they're neighbors. They're practically colliding with each other. The main galaxy is about 76,000 light years across. So we've jumped up from little planetary nebulas that are 2 light years across to something that's in the tens of thousands of light years across. Big, big jump.
And what's really interesting is that this second one is actually colliding with the whirlpool. Like, it's coming from behind. It's not like it's coming on your screen from the bottom, like colliding
from the side, I guess.
From the side, like on the same plane. It's actually coming from behind. So think of that smaller galaxy as being a little bit farther away, and it's coming together. And this process takes countless millions, even billions of years.
Yeah, a collision almost seems like it's way too simple a way to describe it, because it doesn't happen that it's not 2 billiard balls hitting each other where the M51b will just hit M51a and they'll all just fall apart or something. No, what's going to happen is that since these things are kind of diffuse, galaxies are just collections of stars and clouds of gas, what's going to happen is that M51b is going to kind of reach M51a and it'll kind of pass through it. And the gravitational interactions between the 2 will kind of deform the shape of both, but otherwise it's like 2 clouds passing through each other. And it's going to try to pass through almost all the way, but then the gravity is once again going to try to pull it back. So it's going to rock back towards M51a again. And these 2 are just going to wobble around each other in the same place until they likely will probably form one big galaxy that's a combination of the two. That's going to be the final result of the collision, one beautiful marriage of these two galaxies into one thing.
Oh.
That's why it takes so long. Because
Yes.
it's just, for a long time, they're just going to be oscillating back and forth, changing shape over time to create one new thing.
Yeah, truly, truly epic.
Mm-hmm.
I'm just getting it back to the awesome spiral, because it looks so good, right? Like, it just looks so good. But yeah, it's a very far away galaxy as well. I think, did you mention the distance?
The distance to this galaxy is about 23.5 million light years away.
That's million with an M.
Yeah.
Mm-hmm.
So, as before, we are seeing this object as it was in the past. So, because this is 23 million light years away, its light has taken 23 million years to reach us. We are seeing this galaxy as it was 23 million years ago. Now, at this point you might be asking, well then, isn't there a chance that it's just completely changed shape by now? What if something happened? What if it got destroyed? Maybe it's shaped completely different. Will we ever know? But once again, you must account for the fact that things out in space work on much longer and larger time scales. So, while 23 million years for us is a long time, for a galaxy it's not as much. While it's true that these galaxies may now be at a slightly different stage of their merger, overall the shape might not be all that different.
Just to address one comment from Kurt, how does this compare to the size of our Milky Way galaxy? Well, Whirlpool is about 76,000 light years in diameter, actually more like 77,000. The Milky Way is about 100,000 light years. So let's say just on your screen here, the left and the right side of the galaxy, so that's our 77,000 light years. Milky Way would kind of come out to this bright star right here, abouts. So from this star to this side of the galaxy, that would be our own. So we are a bigger galaxy. But just for the astronomy people, everyone in the chat here, what's really awesome is we see that nice bright nucleus, and we see kind of like these gaps in the arms as well. Kind of like there, dust lanes. These are nebulae, or dust clouds that are within the galaxy itself, blocking out some of the light from the stars.
Yeah, the objects that we've seen previously, the nebulas, those were mostly contained within our own galaxy. So these small 2 light year cross objects are within our own galaxy. But that doesn't mean there are no nebulas in other galaxies. Other galaxies definitely contain them too. So theoretically, if we were able to look really, really close at this galaxy, we would probably find equally interesting planetary nebulas and stellar nurseries and all that. It's just a little bit harder because this is far, far away, and nebulas, being clouds instead of bright, bright stars, are a little bit harder to see. They don't offer us as much light to work with, but you could still see the dust and the gas in there that would indicate that they, in all likelihood, exist there.
In a galaxy far, far away, if you will.
Oh, I think I will.
But yes, amazing, amazing thing. And again, this galaxy and our own are but one of countless trillions of galaxies in the known universe, with their own stories, with their own conflicts, all sorts of history waiting to be discovered.
Yeah.
Okay, is it time?
Is it?
For the Saturn, for the planet.
Alright, let's take
Is
a
it
little bit
time?
of a break from getting further and further from our beautiful Earth. our beautiful solar system. We're coming back now.
We're getting too far.
Yeah, we're getting scared.
Yes.
We're going back home.
It can be a little dark out here. Well, not dark. It can be a little intimidating out here.
Yeah, so we're going to go back to our own stellar neighborhood. We're going to our solar system, and we are going to look at one of our gas giants that we can see around us. Now, Saturn is our second closest gas giant, the famous ringed planet, named after one of the many, many Greek gods. I believe he was actually a Titan.
Oh, I think this is Roman gods, I think.
Yeah, well,
Jupiter.
it's the Roman name, yeah.
Oh, Roman name, yes.
Same gods, different names. So Jupiter, Zeus, Saturn.
Saturn, yep.
Saturn. Anyway, his father.
Really, really cool.
Yeah.
Okay, and I'm just leaving it on here. I'm not going to clear the photos just yet because the dome is still making its way over. But let's see. But for all those imagers out there, what's part of image processing, if you want to take really great images of galaxies and nebulae stuff, is you do have to be aware of the overexposure you might get from imaging the nucleus of these galaxies. So part of the process, that's weird, is you do have to kind of dim the center of the galaxy so it doesn't overexpose and outshine everything else. Kind of a tricky business.
Yeah. Get the fiddly parts.
Okay, now
these beautiful photos.
Exactly. Here's the thing. Saturn is so bright that I think we might have to take it off live stack. Yeah. Well, I think this might be still dome, but I'm still gonna do it. Let's see what this does.
Get one good image.
Yeah. I guess it should be okay.
Where's our beautiful boy?
Oh, it's because I've
The light curve.
yeah, the light curve is looking weird. Okay, and then it emerges. Okay.
Oh.
So this is 20 seconds exposure, and it looks like a freaking star. So we're gonna take it off live stack, and we're gonna do live view, which means it's still on that. So I need to turn it to 5 milliseconds. Load. We'll go from there. There we go. Okay. So that means I have to increase the exposure time, and it emerges from the darkness.
Yeah.
Beautiful Saturn. Oh, wow. It's even more edge on than from a couple weeks ago.
Yeah. Okay, so what you're seeing on your screen right now looks like an olive with a toothpick stuck through it. And that is Saturn with its rings on edge to us. So Saturn has this marvelous property that as both the Earth and Saturn orbit around the Sun, the orientation of Saturn's rings changes slightly. The angle changes. So we get to observe these rings at a multitude of different angles. And some of the earliest sketches of Saturn as seen through a telescope done by Galileo are actually observations of how the shape of the rings changed over time. One of the first things that I was noticed about Saturn is that, hey, it's got these things sticking out, and those things, they change.
And the thing is, at this, I guess, exposure level, you do see the planet in all of its glory. But if I increase the exposure, and some of you might have seen this when I had it on 20 seconds, let's see if it'll let me do it. I'm trying to see. Yep, there's one. There's one moon, and there's another moon. And I think this bright one here is the moon Titan. Here, I'll zoom in just a little bit more so it kind of looks better. But yeah, Titan. Well, Jupiter. Saturn has. Is it the most moons? I thought Jupiter had the most moons.
I think Jupiter is still winning that competition. However, Saturn still has a lot. So the gas planets, due to their enormous mass, do get a lot of natural satellites. They have a lot of moons, and that includes nice round moons, like we expect a moon to be, as well as a lot of small, more asteroid-looking things. So it is suspected that some moons may have formed naturally around them, and that some are simply asteroids or even failed planets that they picked up on their way around the sun.
Oh gosh, one of the vivid memories I have is well, one thing is back in my early years, from getting into astronomy, I learned a lot about the Cassini probe that was orbiting Saturn, taking these amazing photos. And you know, as with a lot of people, I grew up with seeing photos and data from Cassini and the Cassini-Huygens probe that landed on Titan, and other things. So I was quite tearful when Cassini was reaching the end of its life, and NASA decided to take it onto more dangerous orbits, and they called it the grand finale, with the goal of crashing it into the planet itself. And it essentially, maybe it wasn't on this angle, but essentially it was taking these long, elongated orbits that took it in between the planet and the inner rings. So that's, you don't do that with a brand new satellite. So, because that could be quite dangerous. So it took incredible photos, and it even went through the geysers of Enceladus to collect potentially, or to collect some samples and analyze it, with the ultimate goal that its final journey would plunge it into the planet. Now, the reason why they did this is because they knew it was reaching the end of its life. It was running out of fuel, and they felt it was too risky to leave it in orbit. So, and the reason why it was too risky is because there's lots of microbes here on Earth that can survive the vacuum of space. A notable example is the tardigrades, right?
Oh, yeah. So these little guys, they could reach actually up to 1 millimeter in size, so you could almost see them with your naked eye, but you could look them up. Tardigrades, these marvelous little 8-legged little creatures that we've been sent up to space and survived its vacuum.
Exactly. And they were afraid, or I should say cautious, that some of these extremophiles, as they're called, maybe somehow made it onto the probe and survived for decades in space. So, and they didn't want to contaminate Enceladus or some of these moons with Earth probe or microbes, and that's why they decided to plunge it into the planet, where it can be totally eviscerated.
Particularly, they didn't want to contaminate some of these moons because they have been found to have water on them. So some of these moons are known to have a subsurface ocean, essentially. They are covered with water, and the water is covered with a layer of ice. And we think that that might be a good basis for a surface on which life could exist. Now, if these moons have their own unique life on them,
if,
huge if. However, considering the small chance that it may exist there, we did not want to contaminate it with life of our own from a probe. Now, Saturn, on the other hand, it's a big gas giant. It has almost no solid surface to speak of. If you fell into Saturn, as the probe did, you're going to pass through an atmosphere of hydrogen, and as you keep going down, it'll just be more and more gas and more and more gas, and kind of more of a liquidy gas.
And it'll get more dense.
It'll get more dense. It'll, like the probe, it'll tear the probe apart, and there will essentially be no solid surface to smash into. It is not considered as a supreme candidate for life to be living on it, so contamination is not as much of a worry, and also it almost guarantees the probe's destruction. So
Exactly.
less of a worry on that front as well.
Mm-hmm. But I remember so vividly, I was sitting, it was one of my morning classes here at SFU.
Mhm.
And I was sitting in the class waiting for it to start, and I had the live stream going
Mhm.
from NASA, watching the telemetry of the probe as it was plunging into the surface. And it was just like, and then okay, I'm a bad example. Always pay attention to your professors. But I remember Prof began the lesson, but I'm going, no, I gotta watch it. I gotta see what happens. And NASA had a whole simulation going of what it would look like at that period of time as it was firing its retro rockets, trying to keep the antenna pointed at Earth, broadcasting all of this telemetry until ultimately it flatlined, so to speak. And that was it. No
more Cassini. It served well while it
did
could.
so much work. It was incredible.
It did much more than was expected or strictly necessary. We're all very proud of it.
Mm-hmm.
But on the subject of Saturn itself, getting back to this beautiful planet we're seeing here.
Yes.
Yeah, it is, as I mentioned, it's almost entirely composed of gas, and that main gas is hydrogen. Hydrogen makes up a large portion of our universe. And Saturn, interestingly, Saturn is quite a bit less massive than Jupiter, the other large gas giant that we all know and love. However, despite them being almost the same size, Jupiter is much heavier, and that's a little bit weird. So you'd expect a planet made up out of a lot more gas to be bigger. However, we must consider that gas giants don't work the same way that rocky planets do. Let's say that if there was a rocky planet twice as heavy as Earth, it would be proportionately bigger in size, because piling on more rock for weight also makes it bigger. However, with gas giants, piling on more gas doesn't just increase the size of the planet. Gas can compress. It can squish down. So with Jupiter, what happens is that you add on more layers of gas, and what they do is that they weigh down and crush the layers of gas beneath them. And so the planet doesn't grow quite as big as it would if it were just made of rocks. And so you get a planet which is much heavier than Saturn, but is still in fact not that much bigger.
Exactly.
The rings of Saturn, they are not gaseous. They are made out of various rocky and icy materials. So there's some big chunks in there. So there's some things in there that are up to kilometers across, and there are others that are just specks of dust. The rings themselves are not one solid object. It's not like one gold wedding band. They have divisions in between them. And there are even moons located inside the rings. They're called shepherd moons, and they kind of clear a path for themselves and affect the shape that the rings take on.
And it's actually really interesting that the distance from end to end, so the diameter, is about the same distance as from Earth to the moon. So if Earth was on one end and the moon was on the other, Saturn would fit right in there. It's really awesome.
We should put Saturn in between the Earth and the moon. We should just make that our next project.
It would look it's so cool. It would look so cool.
Yeah, it would probably have disastrous consequences for the orbits and everything. However, for a short while, it would be the coolest thing we have ever done.
Yes. One thing I'll point out. With the rings, it's actually really quite fascinating. Where all of the gas giants have a set of rings. It's just they're mostly made of rock. Jupiter's rings is made out of ice.
Wait, Jupiter?
Oh my god. Saturn.
This is Saturn.
This is
We're
Saturn,
on
people.
Saturn.
We're okay.
Yeah.
Some of us.
We're all good.
Yeah, Saturn's rings are made out of ice, which is the reason why we can see them, because ice is so reflective, right? And this has led astronomers to speculate, why does Saturn have ice rings and everyone else doesn't. Well, one leading hypothesis is that Saturn once harbored an icy moon that got too close. This is called the Roche limit. Roche. Roche limit, where that is the point where the tidal forces between whatever you're orbiting and the object itself becomes too great and it pulls apart that moon or object. And this is probably what happened to that icy moon. It got too close to Saturn, and the literal gravity of the planet pulled it apart, forming a ring system, which is why we can see it now. And because it's actually quite close to the planet, some of these particles are actually in an unstable orbit. And in about 2 or 3 million years or so, Saturn will consume its rings entirely, and we won't be able to see them.
Oh.
Yeah, it kind of sucks.
Yeah. Even then, Saturn will still be a beautiful planet. While its atmosphere is less divided and dramatic than that of Jupiter, it still has some interesting things going on. So its poles actually harbor these hexagonal storms happening. So yeah.
Oh, jeez.
Wonderful thing to look at.
Lovely.
Yeah.
What was I going to say? Oh, last thing, because space is so big, Saturn is about 1 billion kilometers away, which means it takes light about 1 hour to get there.
Yeah.
So, really, really incredible. Incredible distance.
Still seeing things as they are in the past. This is how Saturn was 1 hour ago. And if we want to see Saturn how it is now, we'd have to wait another hour and then check up on it.
Exactly.
Everything comes with a delay.
Quite a long time. Is there other planets that are up, maybe? As we go planet hunting?
I'll double check, but I don't know. Do we want to be brave and venture out into the depths of space again? Look at the Cigar Galaxy.
Yes.
Look at the Sunflower
Yes.
Galaxy, the harder target, but I kind of miss seeing it.
We are explorers.
Yeah.
We need to explore. We're going to venture back out. We'll be daring. And we'll go back out to the depths.
Yeah.
Okay, and then for this one, I have to turn on live stat once more. I gotta go. That's just Saturn. Don't worry about that.
Do not be afraid of the
Don't be
bright
afraid.
lights on your screens. It's normal.
It's normal.
Our planetary luck is bad.
Okay, the dome is still slewing. Getting these bright objects, or sorry, bright images.
The one possible target, Neptune is a little bit above 20 degrees in altitude, so if we want to maybe try to look for that planet later, then that'll also be... Oh, look at that color.
I gotta fit.
Don't worry, space has not become bright magenta all of a sudden.
Oh, I gotta
That's on
zoom
our
out
end.
too.
Oh, yeah.
Okay, I gotta do this. Oh, it's still... Okay, hold on. No. We do
A lot
this. We
going
do
on.
this. Yeah. Okay, that's a little better. Okay, so we're gonna go like this, and we're gonna go like this.
Yeah, someone in the comments has mentioned that soon Earth might have its own ring of space junk. And yeah, that would be a very interesting way of gaining rings for our planet. Space junk is interesting. There is a whole organization dedicated to essentially tracking about, I think, 2,000 of the largest pieces of space junk out there. And tracking them is very important because we've got a lot of satellites around the Earth now. And if any of those satellites have a piece of space junk collide with them, it'll do two things. Firstly, that satellite may break and it'll no longer be providing the valuable services that it does. Secondly, in that collision, more pieces may break off of the satellite and we will just have created more space junk which in turn could crash into more satellites and create more damage. For that reason, you have to very carefully avoid space junk while out in space. That can become harder the more and more stuff we put up there. Now, let's see our stack.
Now let's see.
Are we going back to M81?
Well, I'm gonna see if we can see it, because the thing is, it's looking. Whoa.
Are we trying to route from the Whirlpool to the cigar?
Yeah, I'm just having a look here, because there's definitely the galaxy nucleus right in the center of your screen, but I just need to double check and see. I wonder if there's a cloud passing through.
I mean, I can take a look. Oh, by the way, guys, as you can see, we got our security cameras set up. The top one's for the interior of the observatory, and there are 2 for the exterior. I'm gonna go out and look up through the dome.
See if there's a cloud. So
you guys might be able to.
You're looking Ursa Major. What's going on over there?
Yeah, Ursa Major. So you guys might see me going out right about now. So
let's see.
Yeah, I'm gonna go outside for a second.
Julia will return.
Ursa Major's clear.
It's clear. Uh-oh. Oh no. Oh. Let me just see. I wonder if it's too dim. It's probably too dim for right now. Okay. Hold on one sec. Let's see. You know what? We're just gonna go back. We're gonna go back to the tried and true Whirlpool Galaxy here. Yeah, and we're just kind of coming into the end here, unfortunately. Oh, that might be a little better, actually. Yeah. We do this, and we do this. Come on, yeah. Okay, let's try changing it up a little bit. Just putting in a different load here.
I gotta wave to you guys from the inside of the observatory.
We like to have fun here. Oh, that's weird. I don't have it.
Where is it?
It's not really working here. Okay.
Okay.
But I want to leave with something cool. But I mean, if the galaxies are not working. I guess I think we overextended. I think we gotta go back.
Neptune?
Or we can try Neptune. Let's be daring. Neptune. Let's see. Okay, Neptune's pretty good. Okay. Rotating. Slewing. Yeah, I switched it over. Didn't really do anything. As we're in the black of the warp, heading over.
Yeah, we can take some time to ponder what we've looked at so far.
Exactly.
We've seen things of many size.
Things of gravitas.
Yeah, literally gravity.
And gravity.
Yeah, so
that too.
We have traveled from our own solar system, so Saturn, and we've gone into our galaxy and searched out the nebulas that lie within. So we've seen the Ring Nebula, the Dumbbell, the Elephant's Trunk. We've seen the globular clusters that hang out next to our galaxy. So the Great Globular Cluster in Hercules. We saw M71. And then we went outside our galaxy and actually got to see the Whirlpool, a completely different galaxy from our own. And now we're going to try to look at yet another planet. Oh,
there's
yes.
the
there's
lovely Neptune.
Blue dot.
The other blue dot.
The other. There are several blue dots.
There are. And this one, oh wow. Okay, this one's it's tricky, but definitely that blue is what we're looking at here.
Yeah.
Let me just change one thing. Let me see.
Yeah. Neptune is another gas giant. It's smaller than Jupiter and Saturn. It is the planet which is furthest out from the sun. So, beautiful blue planet named after the Greek/Roman god of the sea. It is it was discovered very, very late due to its distance. It is quite hard to see with the naked eye for that reason. It was discovered by astronomer Urbain Le Verrier, as well as it is considered commercial. But at any rate, it was only discovered in the 19th century. It was discovered by a lot of calculation and then careful follow-up observation with a telescope. At this point, astronomy was very much a technique and instrument-based thing. And so, the different colors of Uranus and Neptune from Saturn and Jupiter essentially boil down to their slightly different composition. So, being further out from the sun, Uranus and Neptune have a larger proportion of ice, and they have a larger proportion of different gases in them. Specifically, methane is a big contributor to this blue color that we're seeing here.
Okay, in the final moments here of the stream, I just turned down the exposure time to see if we can see that lovely blue-green color, and you can see a little bit, a little bit. But okay, just to kind of wrap things up because we are over time here. Thank you so much for joining us on this wonderful journey. We saw lots of great things, as Julia just said. And we hope to see you for in-person Starry Nights. Do you want to say anything else?
Yeah. Once again, we would be very happy to see you guys at our in-person Starry Nights, which are every Friday here in good weather. But if you want to come back online, every last Friday of the month is indeed our live Starry Nights. And while the hosts may change, the targets may change, we will always be glad to see you here and spend the night with you guys.
Yes. Thank you so much to our moderators, Netjat and Matthew. Thank you so much. And Dr. Joanna Wu for helping us out as well. Yeah. We hope to see you again. Thanks so much.
Good night, everyone.
Good night.